In this separations video, I've prepared a practice problem that will ask you to calculate the energy requirement of a single-stage distillation process. I want to encourage you now to pause the video to read the problem and try and solve it yourself first before I go through the solution. I'm going to start my solution now. So I'm going to start by drawing a process flow diagram, and then we'll do the material balances first, and then finally the energy balances. So we've got a mixture that is 25% benzene and the rest toluene. So once again, I'm just going to keep track of the more volatile component. I happen to know that benzene is more volatile. If you didn't know that benzene is more volatile, the problem statement has given you the TXY and the YX diagrams. And by looking at the YX diagram, it's written in terms of benzene. So you know that benzene is the more volatile component. Another way, again, that you could figure it out is by looking at the TXY and looking at the pure component boiling points. For benzene, the pure component boiling point is 80. And for toluene, which corresponds to 0% benzene, my boiling point is about 110. So again, the one with the lower boiling point is always the more volatile. So I've written ZB here for benzene, not component B. So it's a little bit confusing that benzene is component A. But anyway, only keeping track of the more volatile component. Single-stage distillation process operating at 1 atmosphere. The feed is a subcooled liquid at 25 C and 1 atmosphere. And flows at 200 moles per minute. So that is my F. Specify that one of your products must be 85% pure toluene. What is the energy requirement of the process? So I got to fill in some unknown variables here. Problem statement never told me what the temperature was. So that is going to be one of my unknowns. And I also don't have molar flow rates of the vapor or liquid products. But I do know I can calculate what either YB or XB is. So I'm specified that one of my products must be 85% pure toluene. So in thinking about which one that has to be, so should YB be 0.85 or XB be 0.85, or should neither of them be 0.85? The answer is neither, because again, we're keeping track of the more volatile component. So this is toluene, right? So it's going to correspond to whatever product is 85% pure toluene is going to be 15% pure benzene. So these are going to be the same specification, right? Because they have to add up to 100%. So which component or which stream is going to be the one that is enriched in the less volatile component? So 15% is below 25%, which is my feed. And that is going to tell me that my bottoms product is going to be 0.15 mole fraction benzene. And this is coming from the specification. Once again, coming from the specification that one of the products must be 85% pure toluene. So that's it. My process flow diagram is complete. I have 4 unknowns. I'm going to go through and rewrite them in red. And that means I can go ahead and solve. So a couple ways I can go about this. I have access to both the TXY and the YX diagram, so I can use both of them, I think, are going to have a place in this solution. So first thing I'm going to do is use the TXY diagram to find where XB is equal to 0.15. So on my TXY, that is this point corresponding to 15% benzene. If I follow that up all the way till I hit the bubble point curve, bubble point or dew point, that is going to be the bubble point. Yep, and draw a tie line all the way across until I hit the other side. This is going to give me my corresponding vapor phase mole fraction of benzene. So by TXY diagram, I can say that Y benzene is 0.13 by TXY. And then by the TXY diagram, again, I can read the temperature right off the axis. That is 104 degrees C, also by TXY diagram. So once again, the TXY diagram is going to cut down on the number of algebraic steps I have to take. So I haven't actually solved any equations yet, or it doesn't look like I've solved equations. But once again, I'm solving equations graphically, and that's going to speed up my process a little bit. Now to solve the material balances, I'm going to use the YX diagram. And on the YX diagram, this is going to be a situation where I have 2 points. So I know that my YB and my XB have to be on the equilibrium curve because they are coming off of a stage. And therefore, I have to find that point. So the point that corresponds is YB of 0.3, XB of 0.15. This is there. And the other point that I know is I know that XB is equal to YB is equal to ZB. And that is going to be a point that is on my 45-degree line. So ZB, as the problem statement says, is 0.25. 0.25 is there, and therefore I can just connect these points on a straight line. So if this is confusing of why this is, go back to the previous videos and watch those videos again of how I know that these 2 points have to be on the material balance line or on the operating line. So let me draw a straight line between them. Sorry, my tablet wasn't really cooperating with me there. I can now read this slope off the diagram, or I can calculate the slope. So why am I doing this? Remember the equation for the operating line equation is y is equal to minus L over V times X plus F over V times Z. So the reason why I'm calculating what this slope is because I want to be able to calculate what minus L over V is. So the slope of this line, just by reading it off the graph, is rise over run, operating line, rise over run, and I'm going to calculate this algebraically instead of just, I could count squares, but I want a little bit more precision, I think, for this particular problem. So my rise is going to be the difference in my y coordinates. So that is going to be 0.30 minus 0.25 over my run, which is the difference in my x coordinates, which is 0.15 minus 0.25. All right, so working that out on my calculator gets me minus a half. So what this tells me is that L divided by V is equal to 0.5, or alternatively, L is equal to 0.5 times V. Now this is one equation for 2 unknowns, and in order to solve both unknowns, they need another equation. This other equation is going to come from the overall material balance. So I can say that 200 is equal to L plus V, and then I can substitute in for L to say that 200 is equal to 0.5 V plus V, and 200 is then equal to 1.5 V, and finally V is equal to 200 divided by 1.5, or 133 moles per minute. I'm going to go back in and solve for L. Back solving for L should get me 67 moles per minute. Okay, so at this point, my material balance is completely solved. I'm going to go through and redraw my process flow diagram, putting in all known information for the material balance. That is always the first step, remember, of solving an energy balance problem, is solving all material balances first before we can even think about the energy balance part. Okay, here's my updated process flow diagram. I'm next going to make myself that table that is going to facilitate the energy balance process. So I'm going to make my table of my inputs and my outputs and my moles, my specific enthalpies, and my components. Okay, so here's my table, and I just filled in the moles per minute, and I also filled in the table just for my H's. And the rest of the problem is going to revolve around finding what the H's are. So all I'm doing to find these moles per minute is I'm simply multiplying the molar flow rate times the composition of that particular component. And I should find that my balances work out. So for example, I have 50 moles of liquid benzene coming in. 40 moles of vapor benzene plus 10 moles of liquid benzene is equal to 50. So my material balances are working out. Next step is to do the energy balance. So my energy balance equation is going to simplify to Q. I should have drawn a little heating coil here. Q is equal to my delta H. So here's my energy balance equation, and like I said, the rest of the problem is going to deal with figuring out what these delta H's are. I forgot to put in here in my updated process flow diagram that my inlet stream is 25C in 1 atmosphere, and that's going to be important in a moment. So in order to start calculating these H underbars, what I have to do is set a reference state, and each one of these H underbars is going to be relative to that reference state. So as I said in the previous video, a convenient reference state is either the inlet or the outlet conditions. And then I'm not sure if I've said it in this particular video, I've said it before, but just to say it again, the outlet streams have the same process conditions as the process unit. So it's 104C, 1 atmosphere for both. My set reference state is going to be liquid components at 25C, 1 atmosphere. And I said I set one reference state, but you can set technically one reference state per chemical. And it's just better and easier, I think, to keep it straight in my own head if I make it the same reference state. Okay, so if I set my reference state as 25C, 1 atmosphere for liquid, then my enthalpy of liquid benzene at 25C in 1 atmosphere is going to be 0. So that's, again, when you cancel these out, that's how you're making it simpler. Now I need to calculate my H5 and my H6. So I'm going to say that my H5 is for benzene. And because it's liquid, there's no phase change operation that I have to do. H5 is just going to be the integral from 25C to 104C of CP liquid benzene dt. I have to go in the textbook to find what the CP value is. So I am in the appendix of Lane right now, and there's a table that says heat capacities at constant pressure. So I'm looking at the entry for benzene, liquid. I have an entry for A and B, the little constants. I have a minor issue here that the range only goes from 6C to 67C. So that's going to be a caveat of this problem, that I can't necessarily say that the heat capacities that I find in Lane are going to be good all the way up to 104C. So maybe I should look in a different source to find heat capacities. I'm just going to go ahead and use this. So it's not the worst thing in the world. It's a little bit inaccurate, and I feel kind of icky about using heat capacity that is outside of the temperature range for which it's specified. It's sometimes a little bit dangerous to extrapolate data because you really don't know what's going on outside of that temperature range. But again, in the absence of any other information, as long as I clearly state that this is a caveat of this problem, then it should be just fine. So I've got an A constant that is listed at 126.5 times 10 to the minus third. So in your textbook, go ahead and follow along and see where it says that. And a B constant that is 23.4 times 10 to the fifth. To the minus fifth. So remember, this table is a little bit weird that the B constant is listed times 10 to the fifth. And in order to undo it, it's 10 to the minus 5. All right, so working out that integral would get me to 11.2 kilojoules per mole. So go ahead and practice how to integrate this. Just real quick, if you're unsure, if the integral is A plus BT dt, then I'm going to have AT plus 1/2 BT squared. All right, so I just plug that in, plug in my limits of integration, and once again, it should get me to 11.2 kilojoules per mole. Doing a similar thing for H6, where I am now looking up what the heat capacity of toluene is, so I'll challenge you to do that on your own, and you would find that the molar enthalpy in this case is 13.4 kilojoules per mole. And I'll also note that there's no concern about extrapolation for toluene. So in the table in the book, the range goes all the way from 0C to 110C. So the only problem I'm going to have is with the enthalpy of benzene. All right, so just like that, I've got 2 of my H's done. And the last thing to do is to calculate H3 and H4. These are going to be a little bit more tricky. So H3 is the molar enthalpy of vapor benzene relative to liquid benzene. So I'm going to have to construct a hypothetical process path. So I like to think of it of drawing myself a little game board type thing, right, where I have T on this axis. So I'm going from 25C to 104C. Except for benzene, I first have to pass the boiling point, which is listed as technically 80.1, I think is what it is. Yes, that's listed in the table above in the Lane appendix. So I've got vapor and liquid, and I'm going to start at vapor. I'm sorry, starting at liquid at 25 C. I'm going to heat up to 80, perform the vaporization, and then finally perform the final temperature increase. So I've got 3 steps here, 3 integrals to calculate. I've got the integral from 25 C to 80.1 C, which is again the normal boiling point of benzene, CP vapor benzene. So CP for a vapor is different than CP for a liquid. And in that table that I referenced in the appendix, you can find both. I then have to add the enthalpy of vaporization for benzene. And that is something that you can find in, this should be in the textbook as well. Yeah, in my copy of the textbook, it's not labeled. So this is the physical properties table that is in the appendix. There's an unlabeled column in between boiling point, temperature, and specific gravity. That is for the enthalpy of vaporization. So for benzene, this value is given at 30.77. And then I finally have to add from 80.1 all the way up to 104 CP for vapor benzene, DT. And I made a mistake there. This should be liquid benzene. Okay. All right, so now I have 3 integrals to calculate. You can go ahead and do that. I will do that and report the final answer. I get 39.9 kilojoules per mole, which makes sense, right? So my molar enthalpy of a vapor should be greater than the molar enthalpy of a liquid. So I'm comparing this 39.9 number to my 11.2 number from before. And I'll do the same thing for toluene. The only difference is instead of 80.1, I'm using the boiling point of toluene, which is 110.6. So if I do that calculation, I'm going to get 47.2 kilojoules per mole. Once again, I encourage you to go through and do this on your own to make sure that you know how to do it. All right, now I've got my molar enthalpies. Last thing to do is to plug them into my Q equation and solve. So when I plug in these molar enthalpies, I'm going to get moles per minute times kilojoules per mole. That's going to give me kilojoules per minute, which is an awkward unit. So I'm just going to calculate my Q in kilojoules per minute, and then a more convenient unit to calculate, to convert that to is to kilowatts. So I crunched that number and got 6,872 kilojoules per minute. I need to convert that kilojoules per minute, like I said, to seconds. So there is 60 seconds in 1 minute. So just dividing through by 60 is going to get me my final answer in kilowatts, which is 115 if I round kilowatts. All right, so just a sanity check, does this make sense, right? So all 4 of my H's were positive, and that is going to make sense because I'm heating, right? So I have a positive heat requirement. What about magnitude? 115 kilowatts is a lot, but 200 moles per minute is also a lot too. It's kind of hard to contextualize what 115 kilowatts is. It's kind of the best way I know how to do it is thinking about a 100-watt light bulb. So 100 watts compared to 115 kilowatts is considerably more. It's like 1,000 light bulbs. So I'm heating these chemicals from 25C to 104C, and in the process vaporizing some of it as well. So this type of analysis, once again, is going to allow us to then convert this energy requirement into a certain dollar amount. So if I happen to be running this particular process in my garage and I know that electricity costs 9 cents per kilowatt hour roughly, and I can know how long I'm going to run my process, that is going to give me a dollar amount for how much energy I'm going to spend in doing this separation. It's going to do it for this video. I hope you enjoyed watching. I'll see you in the next class period.